Okay, thank you. Okay, it's my pleasure to present our results at this interesting meeting, and thank you the organizers for inviting me. So today I'll talk about imaging topological currents in graphene and twist angle disorder in magic angle graphene. So this picture that you see here is an image of equilibrium currents that flow in the Landau levels in graphene as a function of position and carrier density. And this interesting imaging technique was developed recently by Viram Uri and Samir Grover, and I would like to thank our funding agencies. So let me start first with our experimental technique, which is squid on tip. So we take a quartz tube of about 1 millimeter diameter and pull it into a sharp pipette. And then we choose one of our favorite superconductors and do 3 depositions. In the first deposition, we coat one side, then we coat the other side, and in the last deposition step, we coat the ring at the apex. And as a result, we form a tiny superconducting loop at the very edge of a sharp pipette. So this is one superconducting lead, this is the other. And in the regions where the leads overlap the ring, we have stronger superconductivity, and the gap, we have weaker links, forming a squid, which is ideally suited for scanning probe microscopy. So this is how it looks in scanning electron microscope. This is a squid. This is a lead squid that was developed by Denis Vasyukov and Yoni Anahori. These devices can be as small as 40 nanometers. They operate in fields of over a Tesla. Actually, recently we've developed devices made of molyrhenium in this work, which go up to 5 Tesla. They can have extremely low flux noise of down to 50 nanophinode per square root hertz, a field noise of down to 10 nanotesla per square root hertz. And they're extremely sensitive for spins. So if you ask yourself how many spins we can measure if we put them in the center of this squid, so the answer is below 0.3 Bohr magneton per square root hertz. Namely, we have enough sensitivity to image the magnetic field of a single electron spin in principle. Recently, we have also shown that these devices can be extremely sensitive thermometers with sensitivity of below a microkelvin per square root hertz, which allows a study of dissipation in quantum systems with extreme sensitivity. But today I will not have time to describe the thermal imaging. So today I'll focus only on magnetic imaging. We attach these squids to quartz tuning fork, and we use the quartz tuning fork for force sensing, which allows us to scan very close to the surface of typical height of a few tens of nanometers above the surface. We also take the advantage of the fact that we can oscillate this tuning fork, which means that we can oscillate the tip parallel to the surface with a controllable amplitude of several nanometers. This will become important for our talk today. So in the first part of the talk, I'll describe imaging of equilibrium currents in the quantum Hall edge states in graphene. This work was done in close collaboration with Jürgen Smet and Youngwook Kim from MPI Stuttgart, and theory support from Cyprian Lewandowski from MIT. So when we talk about quantum Hall, the usual picture that we think about is Landau levels, which are full up to the Fermi level and empty above it. In the bulk, we imagine an insulating state in this case, where the electrons flow in closed orbitals. And all the actions happens on the edges, where we have these famous skipping orbits, which allow flow of current downstream, as we call it, along these chiral edge states. So we have one edge that carries current down, and the opposite edge carries current up. And these edge states are topologically protected. And this is the general picture that we imagine. So in this case, we have 2 edge states, one at each edge of the sample. And during the years, there have been quite a number of works that try to image these edge states using either scanning potential techniques or microwaves. And indeed, the edge states were visualized by some of these techniques, but none of them could image currents. So far there was no direct way to image the actual currents that flow in these edge states. So this is what we decided to do. So this is a graphene sample. This is an edge. It is encapsulated in boron nitride schematically. And this is our squid on tip. And all the studies that I will be showing are at field of about 1 Tesla and the temperature is 300 millikelvin. We apply backgate to the device so that we can change the carrier concentration, and the device is grounded. So now let's imagine that we have one edge state carrying this skipping orbits, this chiral currents that flow in the edge state. So if we take a cross-section through this device, we expect to have a narrow strip of current flowing along the edge. This current creates a magnetic field according to Biot-Savart. So we measure the out-of-plane magnetic field. So this is how the out-of-plane magnetic field of this current looks. So you have positive field on one side and negative field on the other side. And it's broadened due to the finite height and the finite diameter of our squid on tip. And in principle, once you measure this entire magnetic field, you can do inversion and to reconstruct the original current. The problem is that this is an extremely non-local signal. So the inversion becomes complicated due to noise and finite size. So it's a non-trivial procedure to do inversion properly when you have limited signal to noise. Alternatively, we take advantage, as I mentioned, of the fact that our tip sits on the quartz tuning fork, and we can oscillate it, let's say, in the x direction with small amplitude. And therefore, we can measure at the tuning fork frequency the derivative of this Biot-Savart. So the derivative dBz dx, this is how it looks. And it turns out that derivative gives a very close reproduction of the original current. And it's just broadened again by the finite tip size, which is a few tens of nanometers up to 100 nanometers, and the finite scanning height. So this allows us to attain a direct imaging of the current. So in this case, we will see this sharp peak in our BZAC signal, which you can think of as directly imaging the current to within the spatial resolution of our setup. So I want to emphasize that in all the data that I will be showing, the graphene is grounded. We don't drive any current through the sample, and all the currents that I will be showing are all ground state equilibrium currents that flow non-dissipatively in the system. So this is our experimental setup. So this is our graphene. This is an edge of the graphene defined electrostatically by a split gate. And we will try to see what happens when we change the Fermi energy through this device. So this is the band structure. These are the Landau levels. We are talking again, this is monolayer graphene. And this is the corresponding filling factors, 2, 6, and so on, with fourfold degeneracy. And we start with close to charge neutrality. So the filling factor here is 0.7. And we see no currents in the sample. There are some currents due to disorder, but unfortunately, I will not have time to describe them. They are quite interesting in their own right. And let's first start increasing the carrier density, filling the first Landau level up to filling factor of 2. So now I show you a movie, what happens as we increase the filling factor. And when we get to slightly above 2, namely we have 1 full Landau level, we indeed observe an edge current flowing downstream. So now the situation is like this. Our Fermi level is here. We expect to see one edge state, which carries equilibrium currents, topological currents, and indeed, this is what we see. So far, no surprises. Now we increase it to the next Landau level. So we are going now to filling factor 6. And you see that the edge states moves towards the edge. It becomes more narrow, more compressed. But surprisingly, this black region appears. Namely, now we have current that flows in the opposite direction. We will call it non-topological current. So again, you should think of it as real imaging of current, and this are even the units of current. So we are now in this situation. We're at filling factor 6. We have 2 full Landau levels with 2 edge states. We expect 2 downstream currents. And indeed, we observe 2 downstream currents, but surprisingly, between them, we have an upstream current, which we usually don't think that exists in the system. Now we go to the next Landau level. For this one, you see these edge states moving towards the edge. They become more denser, start overlapping within our resolution. But again, surprisingly, a new upstream current appears, followed by another downstream current. So now our situation is like this. We have 3 full Landau levels, indeed 3 downstream edge currents, but between them, we have these non-topological currents. And now we go on, the picture repeats itself. Now we have a new non-topological current coming in, followed by another topological current. So the conclusion is, unfortunately, I don't have much time to go into details and explain it, but the conclusion is that the incompressible strips carry downstream currents as expected. These are the skipping orbit currents that we always think of. But surprisingly, the compressible strips between the incompressible ones carry current in the opposite direction with comparable amplitude, which we call these non-topological currents. And it turns out that some 30 years ago, there was a theoretical prediction and description by Geller and Vinale exactly of these currents, but since they've never been observed so far, even though we are 40 years since the discovery of quantum Hall, but now that we can image these currents essentially for the first time, we indeed see that this prediction is there. As I said, I'll be happy to answer if there are some questions in the question time, but I will not be able to describe it in more detail. So now we move to the magic angle graphene. And this was done again in very close collaboration with MIT team of Pablo, Joan, and Daniel. And so essentially we do a very similar experiment, but now on magic angle graphene. So again, we have twisted bilayer graphene encapsulated in boron nitride. We are still at about 300 millikelvin and 1 Tesla. And again, the magic angle graphene is grounded, no external currents, only equilibrium currents that we measure. And we essentially repeat this experiment. And this is what we see. So these are the edges of our graphene structure in a whole bar-like geometry. The red one are the incompressible strips carrying downstream topological current. In fact, if this picture of thinking of current is too complicated for you, you can forget it and just think of mapping compressible and incompressible regions. So the red are the incompressible regions and the dark blue are compressible regions that carry current in the opposite direction. And the first striking thing that you see here is that the quantum Hall edge states appear in the bulk rather than along the edges, as we've seen in monolayer graphene. And moreover, if we now change the backgate, you see that these currents and Landau levels move around, but they actually never reach the edges and never flow parallel to the edges, which is very surprising and quite disturbing. So as I'll describe in more detail later, this arises from the fact that the twist angle varies with position. So for example, if you have a twist angle gradient in this direction, you will form different Landau levels which are forming compressible and incompressible strips parallel to each other. The incompressible regions will carry the topological currents, and the compressible regions will carry the opposite direction currents in the compressible regions. In the monolayer graphene, we've used the tuning fork in order to oscillate the tip in order to create this direct imaging of the current, which works very well, but it has the one disadvantage. If you oscillate your tip in the X direction, you can image the Y component of the currents. You cannot image the X component of the current. So what we did here, instead of moving the tip relative to the edge states, we now apply small AC voltage to a DC voltage on the backgate, and now we move the strips themselves relative to the tip, And you can show that actually with this back AC, the strips move perpendicular to the current direction, and therefore we can image a magnitude of the current for any both X and Y. So now we can actually, so in this case, we should see these 4 strips as very sharp peaks because the current has much higher density in incompressible regions than in compressible, these dark blue regions. So since Dima presented a very nice introduction to magic angle graphene, I will skip this theoretical part, but I will just mention again the flat bands that we have near charge neutrality and the dispersive bands away from it. These are the electron dispersive band and the hole dispersive band. And just an important reminder is that it takes 4 electrons per Moiré unit cell to fill these flat bands, or 4 holes to empty them. And since the unit cell depends on the angle, so if we increase the angle, the unit cell shrinks, and if we decrease the angle, it expands. And this is what determines the NS, the carrier density that fills the flat bands. And it is given by theta, the twist angle square, where A is the interatomic distance. So if we know NS, we know theta, and vice versa. So now if we flip this diagram and look at transport measurements as Dima has shown, this is what we see. So this is the flat band from -4 holes to 4 electrons. And these are the dispersive bands. And you can clearly see the strongly correlated states at integer fillings. You can see Landau-like fans at high magnetic fields. And again, so this is the global transport showing RxX on a logarithmic scale as a function of field and the carrier density. But now let's look at a particular line through this at around 1 Tesla, where we did these measurements here. So this is how the transport looks, again, RxX on logarithmic scale. And at 1 Tesla, you clearly see these correlated states, you clearly see NS, and you barely see some quantum oscillations near charge neutrality, and you don't see any Landau level physics in the rest of the diagram. But now we can do, so this is global measurement. We can do the same measurement locally at a specific position. So if we park our tip somewhere and do this measurement, this is what we see. So these peaks, as we've seen previously, each peak means that an incompressible region has passed under our tip. So you see that the Landau levels are fully developed locally, whereas globally you cannot see them unless you go to much higher fields. So the height of these peaks tell us how much current flows in an incompressible strip, and the current that flows in an incompressible strip is proportional to the gap. So the height of this peak actually tells us the gap, the size of the gap between the Landau levels, and the distance between the peaks tells us the degeneracy. So the zeroth Landau level, 5 minutes, okay, I have to speed up. So the zeroth Landau level is 8-fold degenerate. Here the rest of the Landau levels are 4-fold degenerate. Here are 2-fold degenerate 1. The dispersive bands are usually 4-fold degenerate, but occasionally we see an 8-fold degeneracy. So now let's look more carefully on the dispersive bands. So we said they are 4-fold degenerate, so we know exactly the distance between these peaks. They are 4 times the applied field divided by phi naught. But now if we look at the distance between these opposite peaks, it will be 24 B applied over phi naught plus the 2ns. This is how much carriers we have to put in order to go from -ns to +ns. So if we can measure this distance very accurately, we can measure the ns very accurately. And what happens is that these peaks are extremely sharp. Essentially, they're a single point in our measurement, which is about 1 millivolt apart in the backgate. And the distance between these peaks about 20 volts in backgate. So we have an extreme precision in order that allows us measuring this distance to very high accuracy, measuring NS. Once you know NS, you get the local theta, and we obtain a relative accuracy of about 0.2 millidegrees in the local assessment of the local twist angle, and this is with spatial resolution of 50 nanometers. So this was data at one point, but we can now take a line scan and repeat this measurement, and this is what we see. So this is the position along this line, and this is the backgate, like in here. So if the sample would be perfectly homogeneous, these peaks, each of these peaks would give us a straight line, but obviously you see that the lines change their character quite a lot as a function of position, just few microns. And again, we can repeat this exercise of measuring the distance. So this is our NS line as a function of position. Where the distance is small, we have small NS, the large NS at other places. So we can just trace NS as a function of position. And we see that NS changes by about 10%. And the twist angle is proportional to square root of NS. So we can directly get the twist angle as a function of position, and changes from 1.13 to 1.17 here, about 5%, being square root of NS. So this is the distance between, namely the subtraction between these two lines, but we can also add them and find the middle line, which is the charge neutrality. And the charge neutrality is shifted by charge disorder. So we can also map out the local charge disorder, which is given here. And the charge disorder is about few times 10 to the 10, which is comparable to state-of-the-art graphene devices. So charge disorder is quite small, much smaller than twist angle disorder. Since we know the NS and the charge neutrality, we can also trace the integer fillings. And what we see that the Landau levels are very robust in the dispersive bands and near charge neutrality, but they're extremely fragile in the fractional states. So the first conclusion is that correlated states are very fragile with respect to twist disorder. So we saw point, we saw line, but now we can do area scans. So we repeat this measurement over the area, and this is a movie showing the Landau levels in this scanning area. And you see that the Landau levels do crazy things. They're all over the place as a function of backgate. So from this movie, we can do the full 3D tomography of the Landau levels. And so this is XY position and the backgate. And the Landau levels form manifolds in this three-dimensional space. And as you can see, in an ideal sample, these manifolds would be flat, but they're extremely curved, which is the result of twist angle disorder. And again, we can repeat this exercise and now get a two-dimensional map of the local twist angle. In this sample, it varied from 105 to 1.18 degrees, forming very complex landscape. And there are a lot of areas which have no magic angle physics at all. For example, you can see here, no Landau levels at all. If we compare it with AFM imaging, we can trace out the bubbles. So these are the bubbles in the sample, and they completely kill the magic angle physics within the bubbles and within about half a micron around them. But there are also quite a lot of areas which we do not see any features in AFM, and still no Landau level physics, either because of high degree of disorder or because of quite significantly larger or smaller twist angle. So this manifold, this landscape of twist angle is actually a potential landscape for Landau levels because they start from the bottom of the band. So in this case, the Landau levels should originate at the lowest points of this landscape and move up. So now if we look at the movies again, we can trace Landau levels forming here and climbing this potential landscape, forming these, these curved shapes. If we look at this region, we have two minima. So Landau levels should form here and form here. And we have a saddle point. So the Landau levels will form at these 2 points, reach the saddle points, split and move in opposite directions. So you see Landau levels merging and splitting, merging and splitting in opposite direction. Here's another pair coming, merging and splitting. So now once we map out the twist angle disorder, we can now understand better the Landau level physics in these devices. We can also do some statistics. So this is the histogram of this device, showing about 10% spread in the in the twist angle. This is another device. This is the map of the twist angle in this device, and this is the histogram. And we can compare it with transport. So the global transport shows 1.15 degrees for this sample, which fits quite well the middle of the distribution. But if you look at this device, you see that the global transport gives us a much higher value corresponding to this distribution. But once you map out the disorder here of the twist angle, you can clearly understand why, because you do transport on this whole bar and measure voltage between these two contacts, and you particularly map sense the central part, which has a larger twist angle and more uniform. And now you understand why the global measurements do this. I will skip this part. So now you can understand that the transport actually probes the percolation physics in these devices. So for example, this device showed a beautiful superconducting state with zero resistance and finite critical current. And you can understand that here clearly you have full percolation if there is superconductivity between the voltage contacts. Whereas here, we saw a drop in the resistance down to about 300 ohms, but never a zero state or finite critical current. And obviously in this device with voltage contacts here, you will not see a zero resistance state. And also you see that the Landau fans here are much better pronounced than here because there's much less twist angle disorder in the central part of the sample. And also the correlated states are much more fragile. So this is the last slide. So I want to emphasize that the twist angle disorder is essentially a new type of disorder. It is band structure disorder. Namely, in each part of the sample, the band structure will be different. The mass, the effective mass of electrons is different. As you move through the sample, you change your effective mass. And Dima has described the importance of symmetry. So definitely the symmetry breaking will be different at each position, and translational symmetry will be broken and so on. So if, for example, you have one side of the sample that has slightly larger twist angle than the other, this will be the band structure of these two parts. The larger twist angle will have a larger density of states and a broader flat bands. So at zero backgate, all these states will be filled up to charge neutrality, and this will be empty, and there will be no dramatic difference between these two parts. But once you apply a backgate, a positive backgate, you will charge you will fill your carriers up to some chemical potential given by the density of states and the backgate voltage and the capacitance. This part has the same backgate voltage, same backgate capacitance, so you should fill the same density of carriers in this part. But since the density of states is larger, this will translate into a smaller chemical potential. And since the Fermi level has to be equal throughout the sample and should be zero, let's say, if you ground the sample, the change in chemical potential translates into a change in electrostatic potential. And the gradient of electrostatic potential is in-plane electric field. So now you have large built-in electric field in a metallic state, which is opposite to what we usually think. We think metallic states should screen any internal electric fields. Here, the situation is just the opposite. The system creates large in-plane electric fields, and moreover, these in-plane electric fields are gate tunable. So if we do some simulations going from 1.1 degree to 1.15 over 2 microns, comparable to our experimental situation, this will be the change of the potential based on band structure calculations. This will be the in-plane electric field, which is an order of kilovolt per meter in a metallic state. Carrier density change will be very small. But now if we apply a magnetic field, the Landau levels will have a gradient due to change in the chemical gradient of chemical potential. And as a result, you form compressible and incompressible strips, and extremely narrow incompressible strips of about 40 nanometers. And the chemical potential will jump over these. This will give you quantum Hall edge states in the bulk of the sample. And you have very high electric fields in the incompressible strips up to about 100 kilovolts per meter. This will translate in the topological currents flowing here. So these are the sharp peaks that we measure experimentally. Every time an incompressible strip passes under the tip, we have this sharp peak. And again, charge is quite uniform. These are very small numbers. So and Dima mentioned the dispersive bands, that there are two bands that are almost degenerate, but they are not. So each of them is fourfold degenerate, but occasionally they will cross, as Dima showed very nicely in experiments. And when they cross, we will have accidental eightfold degeneracy, as we see locally in our measurements. So just to summarize, so twist angle disorder is very different from other types of disorder, having very unique, and much of them are counterintuitive properties. So let me just thank the people who did the work. So the scanning imaging was performed by Aviram and Samir. The the squids were fabricated by Kosik Begani, the MIT team, in which we worked very closely, band structure calculations by Mikito Koshino, Pingwu Kyum, and Alex Cross, the single graphene from MIT, the boron nitride from NIMS, and the superconducting electronics from Martin Huber. Thank you very much for your attention, and I will leave you with these movies.
Thank you. Thank you very much, Eli, really, for this exciting talk. This tomography is nothing short of spectacular. And I'm sorry you didn't have enough time to show everything you wanted to show. Next time, we'll give more time to the speakers for sure. We have time for one quick question. Please indicate in the chat if you wish to ask something. Before someone does, Eli, just to verify, as a theorist, we don't take this disorder into account, certainly not enough. So if I understood the images correctly, you have a variation of about 10% in the twist angle over micron distances?
Exactly. So this is 1 micron. So you can see in both samples that we measured out more accurately. So the typical gradient is, let's say, 0.1 degree over a couple of microns. But this is the slide that I skipped. So this is just numerical derivative, because we have such high sensitivity, we can simply take the derivative. And you see that the twist angle, it looks as if it changes smoothly, but actually it mainly changes in steps. So you have some smooth gradients and then steps, which are essentially just a sort of network of stacking folds that you have to release the energy, right? So it's having twist angle variation costs you a lot of elastic energy. So the system prefers to have some network of stacking folds where you change your twist angle abruptly, and then mosaic. You see in both these samples very clearly.
Francois had a question, please, Francois.
Yes. Do you hear me?
Yes.
Yes.
So you say that those local disorders due to twist angle variations, can you discriminate with strain disorder, which can also be local?
True. So strain doesn't couple. So if you have strain that keeps the area of your Moiré unit cell the same, NS will be the same. So essentially we map out NS. And NS is determined by the Moiré unit cell size, because you have to put in 4 electrons per unit cell. So as long as strain will not change the area of the unit cell, it will be invisible to us. What is visible to us is variations in the unit cell area. So that's essentially the map of the unit cell area, if you want.
Okay,
or square root of this. This is actually a map of square root of the unit cell. Is it clear?
Yes, thank you.
Okay, I don't see other questions. Eli, on behalf of everyone, thank you again for this very exciting talk.